Okay, let's begin our lesson. So before we begin our lesson, let's do a roll call, okay? So please log in your Lumio and we do a roll call. 好，请同学先登录 Lumio 后，我们先点名 ，OK？ We do a roll call, okay? We do a roll call right now. Okay, let's begin our lesson. So right now, we are going to talk about the second processing step of the photolithography. The second processing step is spin coating PR. So the next slide, the page 13. On this page, we show you the purpose. There are two purposes for the photoresist. Okay. The first one, we want to transfer the mask pattern to the PR or to the PR on the top layer of the wafer surface. Okay, we want to have the same pattern of the mask to the photoresist. So the mask and the photoresist, we want they have the same pattern. We want they have the same pattern. Okay, and the second purpose, we want to protect the underlying material during the subsequent process during the subsequent processing like the etching or ion implantation. Okay, like the etching or ion implantation. Okay, after we do the photolithography, and the next processing step will be etching or ion implantation. So the purpose for the PR is to protect the underlying material, like the silicon dioxide, the gray region, we mentioned. Also, we want to protect the underlying material during the next processing step. Okay, so that's the reason. So we want to achieve the accurate the photoresist thickness and the uniformity is very important. Okay, for the photolithography, you need to have the uniform thickness and of course the accurate thickness. Okay. The next one, we are going to talk about the photoresist. But here, I don't want to spend the time for the negative resist. The resist here is the photoresist. Resist here means the photoresist, 光阻, photoresist. Okay, because right now the IC fab use the positive photoresist, 正光阻. It means the mask pattern is the same as the wafer image. The mask pattern, the mask image is the same as the PR image. This image just means the pattern. Mask pattern is the same as the PR pattern. It's the positive photoresist. Okay, so the exposed PR means exposure to the UV light. Okay, exposed PR will become softened and is soluble in the developed process. Okay, or the exposed PR will become weaker. So after the developed process, all of this PR, exposed PR, will be removed by the developed process. Okay. So finally, developer 显影液developer removes exposed photoresist. Okay. Later we will see that. Okay. So let me show you how this is the positive photoresist. So just as we mentioned, so you see how the PR pattern, how the PR is the light blue color. PR pattern is the same as the mask pattern, right? PR pattern is the same as the mask pattern. Why? Because only the central PR, you see the central PR here, is the exposed area. Exposed area means exposure to the UV light. Okay, So the central PR will become weaker. It will become weaker, soften. So this central PR, this area exposed to the UV light are dissolved in the developer. OK， 最后这些有照到光的光柱它就会溶解在显影液里面。The areas here, the central PR exposed to the UV light are dissolved in the developer. Developer is here. 显影液 or developer here. Okay. This is the positive photoresist. So we only talk about positive photoresist, okay? But today, many years ago, 20, 30, not 20, 30 or 40 years ago, we use the negative photoresist because it's cheaper. Many years ago, over 50 years ago, long time ago, 40 years ago, long time ago, we use the negative PR because negative PR is more is much more cheaper. It's cheaper. Okay. So at that time, you see, today if I want to have the same pattern, but you see how the mask is opposite. The mask pattern is opposite to the PR pattern. Okay. The mask pattern is opposite to the PR pattern. 光照的图案跟最后做出来这个 PR 的图案是相反的，这个就是负光柱 ，OK？ Negative PR means the mask pattern is opposite to the photoresist pattern, okay? So only the central region we use the chlorine, okay? So no UV light can pass through the central region. Only the edge region, or we can pass through the UV light. Okay. So you see, only the edge region, and only the edge region we have the UV light. So the area, like the edge area exposed to the UV light will become cross-link. It means for the negative PR, if the negative PR exposed to the UV light, it will become cross-link. Cross-link means the bonding becomes stronger. For the negative PR, if the negative PR can expose to the UV light. So only the edge region, the PR is stronger. So later, the edge PR can resist the developer chemical, OK？ 所以只有最外层的这个光组，它照到 UV 光，它变得更强壮，因为它是负光组，它变得更强壮。为什么变更强壮？因为它的键结变成是 cross link 的这个键结，所以它的这个键结变得更强壮。所以在之后的显影。在之后显影制成里面，它放到显影液的时候，它不会被溶解在显影液里面。So only the edge PR, this area is exposed to the UV light. So the edge PR becomes stronger, become cross-link becomes stronger. So later, when we use the develop process and all of this area, the PR will remain, because PR can resist the developer, so the PR can remain, okay? So today, if you want to use the negative PR, you need to know, the PR pattern is opposite to the mask pattern, okay? So I put the positive PR and the negative PR on the same slide for your reference. Today, if I want the same pattern, of the PR. So you see, for the positive PR we use, you see, for the mask, the photo mask, has the same pattern as the PR. However, for the negative PR, you see, for the photo mask, the photo mask pattern is opposite to the pattern of the PR. Okay, so you can tell the difference by using this slide. Okay. But summary is this page. I only show you this page. Why right now, nowadays, why do we use the positive PR? Because the most important is we have the better contrast 对比，这个对比指的是 resolution. You can say better resolution. Okay, because for the target, I only want the PR here. I only want the PR here, okay? This is our target. I only want the target, the PR look like this, okay? I don't want the slope worse. I don't want the slope worse or the slope worse like this, okay? I don't want the slope worse like this. I want a very sharp worse or like the positive PR, okay? Because I want to have the better resolution of the photolithography. And nowadays, due to the smaller transistor, of course, the light width of the PR will become smaller and smaller. So of course, we cannot allow to have the slope worse like this. We need to control the light width because the light width for the PR is also very small. So in order to have a very sharp words, okay, and also improve the resolution, so we need to use the positive PR. So for when the technology smaller than 3 nanometer, 40 years ago, I mean, many years ago. So when the technology smaller than 3 nanometer, we begin to use the positive PR. So until right now, I believe if you are working in IC fab, you will use positive PR only, okay? Okay. But I also write down the cross-section view of the photo mask, okay? So how about the mask? Today, if I want you to draw the mask, can you do that? If I want you to draw the mask for the final turn exam, can you do that? I mean, if I give you the target pattern of the PR, can you draw the cross-section view of the mask by yourself? So you see, for the positive PR, the mask has the same pattern, right? The mask has the same pattern of the PR, right? So where is the UV light? The UV light is here, right? The UV light can pass through the quartz, but UV light cannot pass through the chlorine, right? So therefore, only the central PR can be remain on the fin, right? So this is the pattern of the mask. The pattern is the same as our pattern of PR, okay? How about the negative? How about the negative PR? For the negative PR, we mentioned right now we only focus on the cross-section view of the mask, okay? So if I want the central region of have the PR, so our mask must look like this. So the central region, we need to expose to the UV light, right? The central region, we need to expose to the UV light, right? In order to make sure the central PR will become cross-link, or the central PR will become stronger. So the central PR must be exposed to the UV light, okay? So today, if I give you the PR pattern, if I tell you this is the positive PR, can you draw the cross-section view of the mask by yourself? Okay, you need to do that. Okay. Okay. So the next one, the next one, I put all of the 8 processing steps for you. Right now, we already finished HMDS vapor prime and also PR spin coating. And right now, we are going to talk about the soft bake. After we do the PR, after we do the PR coating, then we are go through the soft bake. Okay. So when you see the soft bake, right now see the figure first. Okay. See the figure first. It's also a very simple process, right? You just put the wafer on the hot plate, right? If you put the wafer on the hot plate, of course, we have the higher temperature, but only 100 degrees Celsius, okay? I only memorize around 100 degrees Celsius. It's good enough. Just remember 100 degrees Celsius, okay? So you can remember for a lifetime, right? Don't try to remember 90 to 100 degrees Celsius. Just remember 100 is much more easier for you. So for the soft bake, it's around 100 degrees Celsius. Usually the duration is very short, like the 30 seconds, several less than 1 minute, less than 1 minute. Okay. So you put the silicon wafer on the hot plate, 100 degrees Celsius, and it's around 30 seconds. And the purpose for the soft bake, you see the purpose is very similar, right? We want to remove the solvent, or we want to remove the solvent of the PR, okay? Because right now we already have the PR, so I want to remove the solvent of the PR. Why do I want to remove the solvent of the PR? Because I want to improve the adhesion between PR and the wafer, of course, right? Because the adhesion is very important to improve the adhesion between PR to wafer, okay? So of course, like the purpose for the HMDS vapor prime, and also the purpose for the soft bake is to improve the adhesion between PR and the wafer, right? So you know how important of the adhesion ability of the PR to the wafer, okay? So not only the soft bake, but also the HMDS vapor prime, we have the same purpose, right? Like the first vapor prime and the third soft bake, those two processes, we want to improve the adhesion between PR and the wafer, okay? We want to improve the adhesion between PR and the wafer, right? Okay, so they have the same purpose, okay? So that's the reason for the soft bake, I want to remove the solvent of the PR because I want to improve the adhesion ability. Also, we can improve the PR uniformity, okay? We want to improve the PR uniformity, okay? Okay. The next one, alignment and exposure. Alignment and exposure, we must spend a lot of time. Yes, I think maybe more than 1 hour because right now when we talk about photolithography, alignment and exposure, I think it is the most important session. Many technology is inside the alignment and exposure here. So we will spend more time in the alignment and exposure of this chapter, okay? So right now we already have the soft bake. Right now we need to do the alignment between mask and the silicon wafer. After we do the alignment, we turn on the UV light to do the exposure, 曝光 to do the exposure, okay? So for the alignment and the exposure, nowadays, I mean in the IC fab, photolithography is based on optical lithography. For some lab, for some school, they can use the electrical lithography, but it's not in commercial scale. It's not a commercial scale. If we are talking about the commercial product like the IC fab, of course, they need to use the optical lithography because they need to know they need to know after they finish all of this processing step, they need to know they cannot waste too much time. So that's the reason in industry they cannot use the electrical lithography. They need to use optical 光学的曝光我们是照光嘛，是用光学的方式来做黄光为影。你看我们是照 UV 光，所以它是一种光学的方式，它不是用电子束的方式业界通常它不用做量产，它做研究做研究你在很小的区域里面那也没有时间的压力，没有量产的压力，没有成本效应的压力，你可以用电子束的方式来做曝光。In school, you can use the electrical lithography. However, in industry, they only can use optical lithography for many factors. Okay, so optics is very important because all of the photolithography is based on an optical image process. Okay, so the process including refraction and refraction of the light are used in optics. Today, if we have the lens, for example, if we have the lens, the first refraction means if you have the UV light, another UV light will have the refraction, right? And how about the other refraction? How about the other refraction? It means after we have the first incident light, then it may, this is the second refraction. The second refraction means the light will pass through the lens and change the angle, also change the angle, change the angle. So this is the first refraction, 反射. And the second refraction means this light, the incident light will pass through the lens and change the angle, the angle. This is the different angle. Okay. So 第二个光是折射，这个是折射，一个是反射，透过反射跟折射。你就看它的光有没有穿透过透镜嘛，没有的话就是反射，有的话就是折射。Okay. It's very simple, okay, right? The first one, if the lens just like the mirror, so it's like the reflection. And if the incident light is passing through the lens, it will go through the second reflection, okay? But I don't talk about the optical lens. We don't talk about this, okay? So we also have the different type of the lenses, like the convergent lens or divergent lens, different kinds of lenses we are using, okay? So today we want to generate the UV light by the mercury lamp here, okay? We can generate the UV light here, we generate the UV light here. And this UV light will pass through, this UV light will pass through so many optical filter, mirror, lens, pass through many mirror or lens, okay? And finally, we have our reticle here. Finally, this is our reticle. Reticle, right now you can remember reticle is the photo mask. Later I will tell you the difference between reticle and the mask, okay? So the UV light is here and pass through many lenses and many mirrors. And finally, this UV light will pass through the reticle here. And then this UV light will also pass through the projection optics. This is projection lens, another many optic lens, okay? And finally, this UV light will be on the silicon wafer. So here is, I believe, silicon wafer. I believe silicon wafer is located here. The silicon wafer is located here, okay? So after the UV light pass through the photo mask, the reticle here, the UV light will pass through the projection optics, then on the top of the silicon wafer, okay? So it's a very complicated process of all of this optical lithography, okay? But we just talk about we just talk about the introduction of the lithography. Okay. So the next one, I will show you. Right now we do the alignment, right? For this step, we need to do the alignment. So alignment is important for the resolution, 解析度, for the resolution, the resolution of our target, right? I mean, for our target, I want our target has the line width about 30 nanometer. It means I just want 13 nanometer. I don't want 31. I don't want 29 nanometer, because resolution tells you I want 30 nanometer. It's our target. The same thing. The line width is 30 nanometer. Okay. If 100 nanometer more or 100 nanometer less, it's not. It means you don't have good resolution. Okay. So not only the line width, but also the overlay. Overlay accuracy is very important. What does that mean? Overlay. So today, alignment is important because I want the accurate line width. I mean exactly the same length, exactly the same width. And also another requirement is the overlay. Overlay. What does that mean? The overlay. Let me give you the example. Today, if you have the three layer of the cake, think about if you have the birthday cake. This is the first layer, right? The central point of the first layer of the cake is here. How about the second layer? The second layer of the cake, you must align here, right? Or the central point must be in the same location, right? The same X location, right? Or the same X location, right? How about the third layer? Likewise. The central point is here, right? The central point is here. So for the cake, I want the three layer of the cake. The central point is and the same X value, right? So it means they have a very accurate overlay. They can overlay very well, okay? Because they can align together the first layer, the second layer, and the third layer. They can align with each other because their central point is within the same X location, right? The central point is the same, okay? So I mean 1, 2, 3, 3 layers of the cake. The overlay is very small. Overlay is very small. It means the resolution is good. Because the overlay is very small. And what does that mean? Overlay. Let me give you another example. Today, if you want to deposit something, right, like the first layer is here, the central point is here. But however, your second layer is located like here. So the central point is here. Okay, right? Or if the second layer, if the second layer is shift to the right, right? The second layer is shift to the right. So what is the overlay? Overlay means here to here, right? The distance between two center points is the overlay. Is the overlay. Okay. So this overlay, we want the overlay is smaller the better, right? Smaller the better, right? The first layer, the central point is the red one, and the second layer, the central point is the orange one, and the gap, the distance gap between the first layer to the second layer is here. So this is the overlay. So we want the overlay is smaller is the better. For this cake, the overlay is 0, right? So for this 3 layers of birthday cake, the overlay is 0. It means the 3 layers can align to each other very well, right? So today the overlap just means you can compare with the different layers, and we want all of the layers they can stack together. And overlay must be smaller the better. We want the smaller overlay. Okay? And usually the overlay we have the X duration overlay or Y duration overlay. Okay, So for the overlay, we have the X direction or Y direction overlay, okay? Or right now, all of this birthday cake or the same thing is from the position view, right? From the position view. And today, if you want to see from the top view, you can also draw from the top view. From the top view, for example, if this is the first layer and the central point is here, and how about the second layer? For example, the second layer, if the second layer is here, the second layer is here, you see? The central point is here. So you see, from the top view, right now we are talking about the top view. So for the X direction, you have the X direction overlay. Also, you have the Y direction overlay, right? X direction overlay and the Y direction overlay, okay? It just means the distance, or the distance between those two central points, okay? So we will do the measurement about the overlay. We need to make sure the first layer and the second layer is aligned together well or not, okay? So you need to make sure the wafer is aligned to the mask, very, very, very accurate. And therefore, after you define the first layer, and then after that, you want to define the second layer, you have another second mask. You need to align the second mask to wafer again, okay? If you can do that accurately, then the overlay X direction and Y direction overlay will become very, very small, okay? 所以为什么我们在前面 wafer 对这个 mask 你要对准，你只要对准的话，你红色这一层的位置对了。那当我们要长第二层橘色这一层的时候，你会再换另外一道光照。你换另外一道光照，这道光照再跟 wafer 对准的话，那你橘色的这一层薄膜应该就会两个中心会对得准。所以你只要其中一道制程 mask 跟 wafer 没有对准，不管是红色或橘色，它就会偏移离中心，就会不是在正中心的位置。那你就会产生 overlay。所以不管是橘色或是红色哪一道制程里面，你的 mask 对 wafer 没有对准，你就会产生 overlay。OK。Overlay is also very common to see in the IC fab. So overlay is also the terminology you need to remember. We will monitor overlay very, very often. Okay. And then. After we do the alignment, we will do the exposure. We turn on the UV light, so the UV light can pass through the mask to the wafer. For this step, we can activate the photosensitive component of the PR. PR 里面有一些感光的元件，PR 是有机的材料，它里面有一些感光的元件，所以只要我把这个 UV 光打开对正光组而言，这个光组正光组碰到 UV 光它的见解会变弱；负光组它碰到 UV 光，它的见解是变强它会产生 cross link， 所以它见解会变强。When you turn on the UV light, all of these photosensitive components in the PR will be changed. So for the positive PR, if all of these photosensitive component of the PR to the UV light will become weaker. Okay, so we can transfer the mask image to the PR image. Okay, and the next page, I will show you the difference between mask and the reticle. Okay, so you see, the mask size is the same as the wafer size. Okay, the mask size is the same as the wafer. The mask size is the same as the wafer size. It's equal to the wafer. So today you see, that's the reason. I mean, how can I say? The wafer size is not so. So for example, if you use 4-inch silicon wafer or the 6-inch silicon wafer, you can use the photo mask. You can use the photo mask. because the photo mask, you can fabricate the photo mask. You can fabricate 4 inches photo mask. You can fabricate 6 inches photo mask. It's still very small, right? It's still very small, only 6 inches photo mask, okay? It's not easy to fabricate, okay? Also, at the moment, the dimension of the transistor is very large, or the transistor of the dimension is very large. So today, for the silicon, we want to fabricate our PR, and the PR is around 100 micrometer. You see, when you use the silicon for the 4 inches or 6 inches silicon wafer, it means your transistor, your capacitor has a very large scale, or like the 100 micrometer, very large scale of the pattern. It's our target. Today, I want the PR have the line width of the 100 micrometer, very large scale, right? Very large. And this moment, right now, how about our pattern? How about our pattern of the mat? Our pattern of the mat, we also need our mask. Right now, our mask PR here. Sorry, not a PR, chlorine. Right now, the pattern of the mask is also 100 micrometer. Okay, can you see that? The mask pattern, the size of the mask pattern, is the same as the size of the PR, right? The size, I mean the dimension is the same, right? And right now, you see, do you think it's very difficult or very easy to fabricate 100 micrometer line width on the mask? It's not so difficult, right? Because it's still 100 micrometer. So when the technology know we can use the smaller silicon wafer, 4 or 6 inches silicon wafer, you see, it means right now, the dimension is so large, like the 100 micrometer, several hundred micrometer. So at this moment, you see, it's very easy to fabricate the photo mask with the same dimension of the 100 micrometer. It's very easy, right? But how about nowadays? Our dimension is only 20 nanometer. How about 20 nanometer? It's so difficult. It's impossible to fabricate also 20 nanometer line width of the mask pattern, right? Because it's very, very difficult. 100 micrometer versus 20 nanometer. It's crazy, right? It's crazy to fabricate the mask pattern with only 20 nanometer, right? So how about right now? Right now, how can we do? We need to change the photo mask to reticle with a reduction ratio about 4.1 or 5.1. What does that mean? So I also give you the example you can understand. So today our target PR, I want to fabricate our target PR with the 15 nanometer. Very small, also very small, right? 15 nanometer. But it's incredible to fabricate only 15 nanometer pattern on the mat. So how can I do? We can use the reticle, and this reticle, you can use 200 nanometer, 200 nanometer in width for this reticle, okay? And then we can using some reduction length, So we have some middle or some length between the reticle and the PR. So finally, this 200 nanometer will become only 50 nanometer on the top of the silicon wafer. So we have some optical lens, the projection lens, the projection 一些投影的一些镜片，we have some projection lens between the reticle and the PR. So right now our reticle have the larger light width. Right now the light width is 200 nanometer. It's much more easier to fabricate the reticle with the larger size, OK? 我们现在曝光，因为越曝越小，所以我们越曝越小，上面的这个 reticle 上面的这个光照越来越难做，你要做一个50奈米的，它根本做不出来，或是它的 resolution 精准度误差都大，但是我今天如果把它放大4倍，放大4倍，放大5倍，我做一个200奈米的，是不是误差会比较小一点？在制程上、加工上，我们的光照也比较容易做得出来。所以我们的光照做到200奈米，我们中间再靠一些 projection lens， 可能一些投影的镜片，可以把这个宽度慢慢缩小4倍、5倍，等它聚焦在 silicon wafer 上面的时候，就是缩小4倍，所以你在你的 silicon wafer 上面最后曝光的宽度就是50奈米 ，OK？ So right now we use the reticle. The reticle because we want to fabricate the large pattern of the reticle. For the process, it's much more easier to fabricate this reticle with the large size. And then due to the projection lens between the reticle and the silicon wafer, so finally, when the UV light is exposed to the silicon, finally, this light width will only 15 nanometer, just the target, just as the target we set up, okay? Also, we mentioned reticle have the reduction ratio about 5:1 or 4:1, to permit a large reticle pattern than what is emitted on the silicon wafer. Okay, so that's the difference between mask and the reticle. But of course, right now we talk about the 12-inch silicon wafer. Of course, we talk about reticle, okay? But today, when you are working for the academic institution or you are working in the school, we still use the photo mask because our silicon wafer is smaller, 4 or 6 inches. You will use photo mask. Okay, so in the future, if you are working for the academic institution, you will still use the photo mask. If you are working for the IC fab, you will use the reticle, okay? But they are the same, I mean the purpose. They have the same purpose, okay? And the next one, because we need to do the alignment and exposure right now, okay? So we call it wafer stapler, stapler. Stapler means we do the step and repeat, step and repeat again, okay? So right now, where is the reticle? Reticle here. For the reticle here, its main contain 1 or more die in the reticle field. This is the reticle field 1 and 2. 1 and 2 die means chip. So you see, right now, for this reticle, we only have 1 chip, 2 chip. So you see, for this silicon wafer, for the 12-inch silicon wafer, if we have the 300 chips, it means for one exposure, I only can exposure 2 chips, right? So it means it requires at least 150 steps, okay? I need to repeat 150 times, right? Because you see, one time I only can exposure 2 chips, right? But for one silicon wafer, we have, I assume we have 300 chips. But one time I only exposure 2 chips. So it means I need to do the step and repeat at least 150 times, right? Oh, you see, for this silicon wafer, one time I only can expose two chips, right? So totally we have 3 chips. So I need to move around this wafer stage in order to let all of the 300 chips to expose to the light, okay? So how can we do that? And first, let me see. And first we need to do the alignment, right? So when we do the alignment, this is the shutter, the shutter. So we need to put the shutter to the right side so we can block the UV light, right? We need to put the shutter to the right side so we block the UV light first, okay? And then we do the alignment. For the alignment, we have the assignment laser, we can use the assignment laser to make sure the mask, to make sure this reticle is in the same place. So we need to use the alignment laser to make sure the reticle and the silicon wafer has the accurate precision, okay? And then after we make sure the alignment is finished, then this shutter is removed. So the shutter is moved to the left. So the shutter we can take out the shutter so the UV light can pass through the reticle and then pass through the projection lens and finally to the silicon wafer surface, okay? So we mentioned the single field exposure. This is the single field, 单次的曝光 single field exposure. It means for this single field exposure, we only exposure 2 chips, okay? We only exposure 2 chips, right? One time we only exposure 2 chips, right? So for this reticle, the chip size is very large, right? Or for the reticle, the chip size is very large, right? But finally, you can see after the exposure on the silicon wafer, the chip size is much more smaller, right? It's much more smaller. And one time, single field exposure means during this time, this exposure, only 2 chips are exposed to the UV light. So the next one, I need to move the wafer stage a little bit to the next region, and then we will do the focus alignment exposure again. We step to another region, and we repeat the process. We repeat the process. We turn off the shutter, we do the alignment, and then we take out the shutter and we do the exposure, okay? So after we repeat all of this process, the second field is also exposure, okay? Then the wafer stage will change. We will move on to the next location, okay? So we will step and repeat the process. This step means we can move our wafer stage a little bit to the next location, and we repeat the process of the focus, alignment, and exposure, okay? So we can finish all of the 12 inches silicon wafer, okay? So until you finish all of the 300 chips, or finally, exposure to all of the UV light, okay? And here, the projection lens can reduce the size of the reticle field, okay? For presentation to the wafer surface, okay? Also, you can later you can read this slide by yourself, okay? 这一页投影片告诉你它的操作的方式它一次只曝光2颗带，那每次曝光的流程就是先聚焦 focus alignment and exposure， 然后做完这个制程之后呢，这个 wafer stage 移到下一个 移到下一个要曝光的这个 location 之后，它会再 repeat 上面的制程，到下一个要曝光的点，它再 repeat 一下这个制程，做 focus alignment and exposure。等这2颗曝光完之后，再移到下一个点，就是 step， 就是再移到下一个点 repeat， 再重新做 focus alignment and exposure。那直到这300颗晶片，这300颗 chip 全部都曝光完成。So that's the reason we call it step and repeat. We call it stepper. We call it stepper. Okay. So that's all for today's lesson. Any question? Welcome to discuss with me. Okay.